Hello, my name is Jared Frank, and I'm a master's student at the Polytechnic Institute of New York University in Brooklyn, New York. In addition to being a student, I'm also a graduate researcher in the Mechatronics Laboratory at NYU-Poly, and as part of the Simulink Student Challenge, I'd like to talk to you about how our lab is using Simulink to interface commercially available laboratory experiments with graphical user interfaces running as applications on Apple iPods, iPhones, and iPads. So let's get started. The 3 iPhone-controlled experiments we're going to demonstrate in this video use experimental testbeds that are commercially available from a company called Quanser Consulting. This first experiment is a 3-degree of freedom under-actuated helicopter experiment. Using an iPhone application developed in our lab, we open a Wi-Fi communication link with a PC in the laboratory and, using the TCP/IP networking protocol, command the position of the helicopter, as well as receive back sensor data regarding the helicopter's 3 degrees of freedom: travel, pitch, and elevation. The iPhone application makes use of the 3-axis accelerometer on board the device to command the experiment like a joystick. The tilt of the iPhone is sent to the Simulink model, where it is integrated in order to provide smoothly changing references to a linear quadratic regulator, which is controlling the elevation and travel of the helicopter. This communication of sensor data and reference commands between the experimental hardware and the iOS application is made possible on Simulink because of TCP communication blocks that are available in places like MATLAB's Instrument Control Toolbox and Quanser Consulting's Quark software, which is a software that extends the capabilities of Simulink in order to run models in real time on Quanser's PC-based data acquisition and control boards. Now let's look at another demonstration. This second experiment is a state-coupled 2-tank system which contains a pump to retrieve water from a basin at the bottom of the apparatus and feed it into the upper tank. The upper tank loses this water through a small orifice at its bottom, which feeds into the top of the lower tank. Using 3-term controllers, we are able to regulate the water level in the lower tank. Using another iPhone application, which contains an animation of the experiment on the right-hand side of the screen, we may use either sliders or a text input box in order to choose a desired water level in centimeters for the lower tank. After pressing the Start Experiment button at the bottom of the GUI, the Simulink model receives not only the reference command with which to regulate the water level, but also a message telling the controller, located inside of an enabled subsystem block, to activate. Notice that not only do labels in the mobile application update with the current values of the water level in each tank, but the animation on the side updates as well, with its levels mimicking the current state of the experiment. This last demonstration of our emerging iPhone-controlled laboratory is an iPhone-controlled magnetic levitation system. Notice how this application also contains an animation which updates itself in real time based on the sensor data it receives from Simulink regarding the position of the steel ball. All this is done using variations of the same iPhone communication Simulink subsystem block made in the lab for the other experiments. Not only does the user have access to the current height of the levitated ball, they also see the amount of electric current in units of amperes that is flowing through the electromagnetic coil. In order to control this system, we implement a proportional plus integral, or PI, controller for the electrical subsystem to regulate this current, as well as a proportional plus integral plus derivative, or PID, controller for the mechanical subsystem to regulate the ball's height. Without Simulink, not only would we not have the opportunity to seamlessly integrate these state-of-the-art technologies, we wouldn't have a convenient and powerful diagramming environment with which to perform controls education, research, and design. And with that, we thank you for taking a look at the work we have done using Simulink.